Everyone, welcome. Welcome everyone to the Coffees Connections workshop. We're really glad you're here, and we're looking forward to a really great interactive workshop throughout the day today. So I have just a couple of bookkeeping things to go over first. First of all, let's see. So, in terms of timing of talks, some of the talks are a little bit longer, the scene setting talks at the first part of the day. So, for example, those are scheduled for like 30 minutes, which we intended to be 20 minutes of talk and then 10 minutes of questions and discussion. And a lot of the talks are 15 minutes, which are designed to be 10 minutes of slides and then 5 minutes of discussion. So on Zoom, it can be a little awkward to try to stay on time. So what we thought we would do is that the moderators of the session would just kind of pop in and interrupt at about 2 minutes to go. So for example, in the scene setting talks, I would pop in at 18 minutes and say 2 minutes, and then the speaker can kind of finish up the slides. And we hope that you don't dig in too far into the discussion session, because while we have some time allotted at the end of the conference, we'd really like it to be focused and interactive the whole way through. So anyway, so that's so there'll be kind of an awkward interruption just at 2 minutes before the talk. So in terms of questions and interactions, we've got a couple things going on at once. We've got obviously the Zoom chat that you're free to use and we'll be monitoring. We also have a Slack channel that will be monitored as well. I guess the advantage of the Slack channel is that it'll be live after the meeting is over, and whereas the Zoom chat kind of disappears. But as always, the best way to make sure you get your question in is to just raise your Zoom hand, in in Zoom itself, and then the moderators will do the best we can to answer to call on you in the order that you ask the question. But we really do want to keep on time. So if we can't get to a question, make sure you put it in the Zoom chat, or put it in the Slack channel, and we'll try to have the speakers get back to you. Okay, well, Bishek, do you have anything to add about the Slack channel? I didn't set that up, so.
Yeah, I'll be monitoring it. And if you have any questions, and if someone hasn't been able to join Slack for any reason, I'll try to post any questions directed at you over here in the Zoom chat.
Okay, sounds good. Let's see. So, the other thing is we are recording the meeting. If per some chance you do not want your talk to be posted on, or the recording of your talk to be posted on the Coffee's website, just let us know, Bishak, Amy, or myself, and I think we can just cut your talk out if you want. But hopefully you'll want it to be posted. This is kind of informal, so it's no big deal. I think it would be useful to have the talks and the discussions online. I think that's all I had in terms of setup. Amy and Bishek, do you have anything you want to add? Okay.
I have a question, Bill. Could somebody put the Slack link into the chat?
Oh, sure. Bishek, do you mind?
Yeah, I'll do that.
Or is it in the email you sent, Bishek? I didn't see it.
It's in the Coffees DSC Slack channel, so I'll try to share it.
Okay, thanks.
And also, I want to thank everybody from all the wildly different time zones from taking the time to be here. That's great. We really appreciate that. Okay, so that's all I had to say. So why don't we go ahead and start with our first talk? And our first kind of a scene setting talk is going to be given by Shin Toirumi, who is from, and correct me if I'm wrong if I get your institutions wrong, from the Japan Aerospace Exploration Agency, and his talk is
Exactly, yes.
and his talk is entitled Realistic Flux Emergence Simulations from the Deep Convection Zone using the R2D2 code. So Shin, take it away.
Yep. So can you see my screen?
Yep, sure can.
Okay, thank you very much. So first of all, thank you very much for inviting me to this nice, great workshop. And I'd like to start from this one. So okay, let me stop the video. Right. So the continued strong flares and coronal mass ejections and magnetic storms in May 2024, and this active region, actually, this is the active region complex composed of 13664 and 13668, produced sorry, yeah, 10 class flares, 14 major semis, and 3 consecutive halo semis, which merged into a complex ICME with an extraordinarily southward IMF. And yeah, so here, so the DST index reached minus 412 nanotesla, which is only behind the famous Quebec event in 1989 and the Halloween event in 2003. And as a result, ori were observed across the globe, even from the central Japan, which is extremely rare, actually, considering the geomagnetic latitude of Japan. And for this event, we issued an HMI Science Nugget number 200, where we found that the emergence of magnetic flux in this active region complex was record-breaking in the SDO era. So please check this out. And also, the Hinode satellite successfully detected the evolution of this event. And the left image is by the X-ray telescope XRT on board Hinode, showing the bright structure in the active region corona. And the solar optical telescope SOT revealed the very, very complex magnetic structure of this active region. And such structures were the key to producing consecutive eruptions from this active region. And right, yeah, so this is the HMI movie for days, and we can see there are lots of emergence events at the same time. And I think I can skip this page, but the following is a brief summary of the Living Review article with timing 1. So yeah, in energetics, the flares are the releasing of excessive magnetic energy or the free energy that is stored in the active region corona. And here, as shown on the right, when the active region corona has the magnetic energy, there's a gap from the potential energy, and this free energy is released through magnetic reconnection and plasma instability during the flares. Well, maybe only a small portion of the free energy is released in each flare event. And then the magnetic energy is converted into various forms of energy like thermal energy, kinetic energy, and particle accelerations. So the key message in this slide is that in order that the active region is flare productive, the magnetic field has to be non-potential. And often we observe helical structures of various kinds like filament, sigmoid flux rope, semi, and ICME, and we can measure magnetic helicity to see how much twist is injected into the atmosphere. And observations have revealed there are many key observational features. For example, flaring active regions tend to have special polarity inversion lines, PILs. And the right movie, this is a Hinode observation of flares in 2006. So this movie shows the expansion of flare ribbons between the two sunspots in the north and south. And so between these two sunspots, okay, this is the vector magnetogram taken by SOT, and this shows the sheared PIL in between here. And actually, the observation shows that the shear polarity inversion line was created by the rotations of the sunspots. And bottom right is the nonlinear force-free field extrapolation, and the twisted magnetic field lines are seen here. And often the magnetic flux ropes are observed above the polarity inversion line as sigmoids in soft X-ray and filaments in H-alpha. And once flare occurs, the flux rope will be developed into a helical magnetic skeleton of interplanetary CMEs. Okay, so as you see, all these structures are the manifestation of non-potential magnetic fields. And let's move on to the statistics. So statistically speaking, the key factors are the area, complexity, and rapid evolution. The area is directly related to the amount of energy to be stored in the active region corona. And the right diagram is the plots of various sunspot groups, in which the horizontal axis is the area and the vertical axis is the maximum soft X-ray flux, gauge flux. And there exists a positive correlation in this diagram, meaning that larger active regions produce stronger flares. But at the same time, we can also see the different symbols indicating the complexity of the active regions. And the top right part of this diagram is filled with red symbols, which is the delta spots, while the beta spots, the green ones, are a simple bipolar region. And delta spots are like where the umbra of opposite polarities are so close and share a common penumbra, and the delta spots are known to produce strong flare activity. So therefore, the second factor is the complexity of active regions. And bottom left, I cited work by Sarah and Amy, where they found that the delta spots have cycle variation. The fraction of delta spots is larger during the maximum, and I will come back to this later. And the importance of the delta spot is well represented by these classical observations. This active region appeared in 1989, and as you can see, a huge penumbra contains positive and negative umbra. And this is very famous active region, and I think you know this event because it produced the strong geomagnetic storm, which caused a blackout in Quebec and damaged the transformer in New Jersey. So now we know the complexity or delta spots is very important. Then we have two questions. So how are these complex shaped sunspots created, and what's happening down there in the convection zone? The problem is, of course, we can't optically observe the convection zone. Well, of course, I know seismology is a promising tool, but here, what I mean is that it's not easy to know what happens down there. Okay, so one possibility is to use the flux emergence simulations, and here is the typical example. We often set a 2D or 3D computational box, and we set a gravitationally stratified atmosphere. From lower part, the convection zone, photosphere, and chromosphere, and the high temperature corona. And often at t equals 0, we set a magnetic flux tube, often twisted one, and by reducing the density from the midsection, and the flux tube becomes buoyant and starts rising. The middle section becomes elevated, and the plasma drains down along the magnetic field lines due to gravity, so the middle section becomes more buoyant and the emergence becomes accelerated, which we call the Parker instability. The flux emergence is a key to a variety of solar dynamical events, such as flares, jets, element bombs, various kinds of dynamical activity. And actually, there have been many attempts to model delta sunspot using the flux emergence simulations. The representative one is the kink tube model, where a strongly twisted flux tube emerges into the atmosphere. And because the twist of the original flux tube is released, two rotating sunspots appear in the surface, which is reminiscent of delta spots. And the second scenario is the emergence of a single flux tube at two locations. This is my work when I was a student. There's only one flux tube in the convection zone. However, this flux tube starts emergence at two locations along the axis. And as a result, in the photosphere, we have two emerging bipoles, and these bipoles show head-on collision at the middle of active region and produce strongly packed delta sunspots, as you see in this magnetogram. And the third possible scenario is the interaction of multiple flux tubes in the convection zone. This also provides the complexity of active regions. The statistics by Sarah and Amy I showed in the earlier slide, they show that the fraction of delta spots becomes larger during the maximum, and they argue that the delta spots may be produced by the collision of flux emergence events, which is more frequent during the maximum. Right, so from these models, we learned that strong twist and the interaction of flux tubes in the convection zone indeed give complexity to active regions. But the story is not so simple. In most of the previous simulations, including mine, the convection zone didn't possess the thermal convection. The convection zone was not convective in my simulation. Also, even in the convective flux emergence simulations, because the bottom boundary was not so deep, so the flux tubes were kinematically injected into the computational domain by hand. So the effect of background convection remained sort of unclear. And one possible approach is to couple a flux emergence model in the convection zone and the model above the surface as represented by Abbott and Fisher, but we took another way. So in order to overcome this issue, recently we used the RTD2 simulation code, which solves the 3D MG equations with realistic radiative transfer and uses RSST, reduced speed of sound technique. And this code was developed by Hideyuki Hotta. And this code can generate deep thermal convection from minus 200 megameters, at the bottom of the convection zone, to the photosphere. And using this code, we insert a flux tube to see what happens. So for example, we found that the inserted flux tube produces active region self-consistently as a result of large-scale convective outflow. And on the right, you can see that in the photosphere, the delta spots are produced via the collision of sunspots. So the top right panel is the case where there are two buoyant segments along a single flux tube. So there's a how can I say, M-shaped emergence, and due to this M-shaped emergence, we have head-on collision of positive and negative polarities. And on the bottom right, you see that above the photosphere, we also observed that a flux rope-like structure was created. So the important thing is this is all natural. So we didn't do anything, just the flux tube and background turbulence produced the delta spots and flux rope-like structure self-consistently. And this time we did a parameter survey on flux tube twist. So the velocity field of the initial background convection is exactly the same. We don't have solar rotation, just the twist of the initial flux tube is different. We have three cases: non-twisted, weakly twisted, and strongly twisted. Right, so this image gives you the impression of the simulations. the top panels are the total magnetic field strengths at t equals 12 hours. The bottom is the field lines of the flux tube at t equals 0. And from left, no twist, weak twist, and right one is the strong twist case. And this is the photosphere. The top is the magnetogram, and the bottom is the emergent intensity seen from above. You can see that all three cases show successful flux emergence. Previous simulations have shown that you need some sort of twist to bring up the flux tube to the photosphere. Otherwise, the flux tube will be fragmented due to the contracting flows and flux tube expansion. However, this simulation shows that under the convective circumstances, it is not necessarily true. I mean, if there is a convective outflow, even a non-twisted flux tube can reach the photosphere. I mean, the large scale upflow supports the rising of the flux tube. And what is curious about this simulation is that even the non-twisted flux tube injected non-zero magnetic helicity. So the top right panel shows the time evolution of total unsigned flux for the three cases. We can see that the non-twisted case, the red one, reaches the photosphere and it shows the finite amount of total magnetic flux in the photosphere. And the next panel, the middle panel, shows the magnetic helicity injected into the atmosphere over time. We can see that the strong twist case and the weakly twisted case show the injection of magnetic helicity. But we can also see that even the non-twisted case, the red one, injects non-zero, I mean, finite amount of magnetic helicity into the atmosphere. And this is very strange. In the convection zone at the beginning, the non-twisted case, the flux tube, of course, has no twist. But in the photosphere, it shows positive helicity. Why? Well, we did a sort of detailed analysis, but please take a look at the bottom right panel. So the analysis revealed that the background convection rotated the magnetic flux below the sunspots and supplied finite helicity. So we have positive and negative sunspots, and there are vertically stretched magnetic kind of pillar of magnetic flux. And because this random turbulence, there were we found sort of the vortices around this vertical pillar, and this vortex motion twisted, rotated the sunspots in the photosphere, and that's why we saw non-zero finite amount of helicity injection into the atmosphere. So we can say that not only the magnetic flux system, but also the background turbulence can supply a significant amount of helicity into the corona. And by comparing to the flare observations, we found that the non-potentiality of the non-twisted case may even explain minor class flares. Okay, so conclusions. The fate of flux emergence is strongly determined by convection, and turbulence can inject a significant amount of magnetic helicity into the upper atmosphere, even explaining small-scale flares, at least in this case. All right, so the final part of my talk is on the SOLAS emission. SOLAS-C is the JAXA's next generation solar observing satellite. And this has two science objectives. One is that SOLAS-C is to understand how fundamental processes lead to the formation of solar atmosphere and the solar wind. The two is to understand how the solar atmosphere becomes unstable, releasing the energy that drives solar flares and eruptions. The target launch is fiscal year 2028 by Epsilon launch vehicle. This is an international mission with huge contributions from US and European partners. In close collaboration with Muse has been planned from the mission proposal. And the onboard telescope is called the EUVST, UV high throughput spectroscopic telescope, which achieves 3 uniquenesses. And one is it has a seamless broad temperature coverage from the chromospheric to transition region, coronal to even to flaring temperature. 2, it has a high spatial and temporal resolutions. The spatial resolution is 0.4 arcsec, and the time resolution is better than 1 second. And 3, it has a spectroscopic diagnosis to derive velocity, density, temperature, composition, ionization, etc. So what's good about it? Speaking of the effective area, on the left, the short wavelength is about 10 times better than the Hinode ice. And for the long wavelengths, it is 30 times better than the Sohor Sumer. And on the right, there are many more spectral lines compared to the Hinode ice. And we will cover all temperature zones from the chromosphere to corona to even to the flaring temperatures with minimum gaps. And it also has the hydrogen Lyman alpha. And for the flare observations, we will concentrate into the reconnection region with high throughput observations. But at the same time, thanks to the improved cadence, we can repeatedly scan the flaring zones. The bottom right panels compare the scan of Solar Sea and Hinode ice. If we use Hinode ice, the eruption is missed. So during the scan, we missed the eruption because it takes time. And well, eruption occurs during a single scan, while Solar Sea enables high time resolution scans to catch the eruption and, of course, obtain the physical quantities. And well, I think I can skip this. And okay, this is the final slide. I mentioned that the key observational features are the area, complexity, and rapid evolution of active regions. Well, I believe Cycle 25 will be a great opportunity to look into these features. And 2, we have been using magnetic flux emergence simulations to understand magnetic twist and interaction, give complexity to active regions. However, in our previous calculations, we didn't have convection, and we wanted to know the importance of the, say, large-scale convection. And 3, recent attempts also show that the turbulent convection determines the fate of flux emergence, and it can supply magnetic helicity to even explain some small-scale solar flares. And this is very surprising. And 4, finally, I explained the Solar Sea, and one of the objectives is solar flares, and I hope we can have a great collaborations. That's it. Thank you.
Great. Thank you so much. That was great. So questions, comments? Irina.
Hi. Hi. Thank you very much for your talk. Can you hear me?
Yes. Hi, Irina.
Okay, good. Yeah, so I have a question and comment. Comment first about helicity, what you discussed. I want to mention our paper in 2010 when we demonstrated natural formation of stable pole-like structure. And actually, our simulation showed helicity comes not just from, say, granulation layer, but also by formation of twisted bundles. And such bundles actually start to interact each other and potentially can produce like additional helicity contribution to your signal. And my question is about one of your introductory slides when we discuss about code, what you are using for this. What I realize, maybe for first time, what in very deep layers, yeah, this slide, slide 22. you see almost near Tachocline region. Flows have about even higher amplitude than near surface layers. How you explain this?
Okay, I see. You mean the typical velocity of the in the simulation, right?
Flows were stronger than near photosphere, but we know it should be way weaker by orders of magnitude. If you look on image on right, you see and dark colors of because no scale and color.
Let me enter the maybe strong the for example in my slide here the velocity the flux growth rate is a bit stronger than the observed values. So this may indicate that the flow velocities in the convection zone in our computational box may be larger than the actual values.
I see.
Mm.
Okay. Thank you.
Thank you.
Sasha?
I'll be very quick. So thanks for a very interesting talk, and I really like your suggestion for collaboration. In fact, we have tools, Matilsky seismology, so we can test these models. If you can make them available, I probably cannot stay until my talk. I'll be showing something relating from observations related to simulations. But if the way you can provide some kind of, data that we can use for helioseismology, I think it would be great, to link your models to observations.
Right, thank you. Yeah, I'm very curious about that. One thing is that we suppressed the sound speeds in this simulation, so that may be one difficulty. However, for a short time period of time, perhaps we can recover the speed of sound to the actual value and see what happens.
We just need mean values, we can generate our own sound speed or just use them, test the structure and flows.
Okay, I see.
This is already for Matthias's models, so it would be interesting to see confirm analytic model.
That's
it's pretty cool. Yeah, provide data.
Thank you.
Other question?
And do you, I mean, inserted a tube and so for example, your non-twisted one and you got helicity during the emergence. This is one instance of the convection. If you inserted it at another time during the convection, do you feel like you get the same result, or do you feel like you need to do a whole statistics out of this thing?
Yeah, that's a very, very important and interesting question. So we tested 100 cases by slightly changing the location of the initial flux tube with exactly the same background turbulence. And so only by changing the initial location a bit, the fate is totally different. So it's a highly strong coupling between the magnetic field and the velocity field. So sometimes magnetic field drives the flow direction, determines the flow direction, and sometimes the flow determines the fate of flux emergence. So it's highly coupled. And only by changing the initial location a bit, the fate completely, the fate is very different. Sometimes we see a very nice flux emergence. Sometimes the flux doesn't appear at all. Even it sinks into the deep down into the convection zone. So we need to test, perhaps we need to test more cases. But of course, there are many parameters like a location, the twist intensity, field strength. So maybe it takes time.
Yeah, that's my suspicion, is that it's very, very sensitive, right? So
True.
I don't know how many of these very expensive simulations we can do to try and figure out all the different cases, but the ones we've done so far are fantastic. So thanks very much.
Yeah, thank you very much. Well, running a single computation is not very heavy. It takes like hours or days. But the thing is it takes time to prepare the initial background turbulence.
Irina?
Thank you, Tomri, for raising very important question. And I have a very short one about your background conditions. When you insert twisted flux, you inserted this in Hydra simulations, or already magnetic flux is present?
Sorry again?
My question is, what is background conditions in a time when you introduce your magnetic flux rope?
Okay.
You insert this in Hydra simulations, or it is already MHD simulations?
It's a Hydra simulation at the beginning. I mean, it's MHD, but the initial field strength, magnetic field is totally 0. And I added the flux tube. So initially, there's no magnetic field.
Okay, thank you.
Amy?
Hi, Shin. Thanks for talking. My question is a little bit non-specific, and that is, you've obviously been studying sunspots and watching the sun for a decade or more. And my question is, what's your favorite paradigm for how sunspots are formed? I mean, do you think they're being formed in the mid-convection zone, coming from the Tachocline and being buoyantly driven up? Or what's your, it's not very specific, but I'm wondering what you're thinking.
Yeah, so Hideyuki tried the convection flux emergence simulation. So you see, my initial depth is only 30 megameters down below the photosphere. And Hideyuki tried the simulation from the bottom of the convection zone. Of course, it takes time because the rising speed is very slow in the deep down. And he waited for months, and eventually the flux stroke breakout. So he couldn't find a successful emergence. So he added strong twist, very, very strong twist. And finally, he got the successful emergence. But maybe that twist is too strong for active region formations. So then we don't know what is true. I mean, if the flux tubes are truly coming from the bottom of the convection zone, or perhaps from the middle of the convection zone, we don't know.
Okay, still a mystery. Yeah.
Thank you.
So thank you very much, Shin. We need to move on so that we stay on schedule here. Our next speaker is our own Loren Matilsky from UCSC, and he is going to talk about perspectives on flux emergence from all the way from the Tachocline to the photosphere. So take it away, Loren.
I'm gonna go full screen.
Okay.
You guys see everything okay? Hear everything?
Yep, all good, all good.
Okay, everyone. Well, thank you for coming out to the workshop, and I want to thank the organizers for organizing what I think will be a great day of discussion. I inserted perspectives from a theorist today because things are going to be sort of biased in that framework, and so I apologize off the bat if I'm less specific. I really want to set the tone for broad general understanding of the problems at hand. So the title picture is basically the order zero question is, why is the sun magnetic? Why are there these bands of magnetism at mid latitudes? This is a picture from UV AIA overlaid. There's about 25 images here, and you can see that the surface of the sun is very dynamic. There's coronal loops, there's magnetic arcades, and that's really the question that I think solar physics is seeking to answer. Everything else is sort of the fine structure behind that. Okay, so I have more disclaimers. I'm a theorist specializing in global modeling. So the big picture that I'm discussing today is going to be sort of skewed by that lens. I encourage you to see Nick Brummel's talk for way more details on actual theories of flux emergence, because that's not my specialty. And I also apologize if I inevitably gloss over very important work. I'm sort of picking and choosing the general features of what I think are the important story. Okay, so let's dive in. What do we know about the sun? And I think it's good to get a broad perspective. I know a lot of us have seen this stuff a million times, but just to set the stage, there's a thermonuclear core in the inner 20% that transports the solar, that produces a solar luminosity that then must be transported to the surface. And in the inner 70% of the sun by radius, this is transported by photons. We believe the fluid is largely stable, and so it's still turbulent, but there's not very much motion. And then we reach the convective zone in the outer 30% of the sun by radius, and there the energy is transported by these bulk overturning motions of the fluid depositing their heat. And it's really this convective engine that's driving most of the activity and the dynamics that we observe. And then finally, again, there's this very thin layer called the photosphere, where the photons are able to escape, and then they reach the rest of the solar system. And that's the light that we see from the sun. What do we know about the solar magnetic field? Well, to remind everyone, we really can only observe the surface magnetic field with great fidelity. So again, this is a UV image from AIA that shows these complicated surface features of the magnetic field. And what we know about the surface magnetism is that in general, the magnetic flux is very filamentary. It comes in these flux tubes. The flux tubes only cover about 5% of the solar surface at any given time. So most of the sun is quiet, except for these concentrated regions. There are both small flux tubes called magnetic elements and large flux tubes, which are active regions, also associated with sunspots. We know roughly the direction. There's nearly radial or vertical field lines within an active region, and the field strength is nearly homogeneous, around 1 to 2 kilogauss. And so the question that was already raised is basically, where are these flux tubes coming from? Are they coming from just below the surface, deeper in the convective zone, or the tachocline? The other thing we know is that this is a dynamo process, and on average, the surface magnetism is very well ordered. So this is the famous butterfly diagram. It's the longitudinally average field as a function of time on the x-axis, and latitude on the y-axis. And what you see is that there are these bipolar magnetic regions. So this longitudinal average picks out the polarity of the leading active region. And so there's a positive polarity, the yellow in the figure, and then the trailing polarity is a bit further from the equator. And the pattern of emergence makes these butterfly wings, and that's why it's called a butterfly diagram. And there's many different features of order to this plot. There's Hale's polarity rules. The northern hemisphere at any given time has an opposite polarity sense to the southern hemisphere. There's this 22-year cycle, and so these activity cycles, which are 11 years, reverse the polarity sense in each hemisphere between adjacent cycles, making a 22-year cycle overall. There's the butterfly wings, the equatorward pattern of emergence. And then there's Joy's law, where these leading spots are of the opposite polarity than the trailing spots, and the trailing spots get swept to the poles during cycle minimum. So this is really an intricate structure. And so I would say, I guess the order 0 question is, why is the sun magnetic with the magnetism appearing at low latitudes with the exclusion zone at the equator? And then the first order question, really the heart of the problem, is the solar dynamo. Sorry, there's a lot of traffic, so I'm just gonna close the window. Why is the solar dynamo so ordered? And I like to say that if you answer these questions, then maybe you get a Nobel Prize. Okay. The other thing we know about the sun from helioseismology is the rotation rate, which must be intimately coupled to the dynamo. And again, the observations have yielded a number of surprises. So there's strong latitudinal differential rotation. This was known since Galileo. And in this plot, I'm showing Rachel Howe is showing the longitudinally averaged angular velocity as a function of radius and latitude in a section of the meridional plane. So the fast is red, blue is slow, and this differential rotation propagates all the way through the convective zone. At the base of the convective zone is what's called the tachocline. There, the differential rotation rapidly transitions in this narrow layer, which I think is about 2% of the solar radius, thick, and it transitions to rigid rotation in the radiative zone below. There's another shear layer close to the surface, the near surface shear layer, where the differential rotation drops by about 5%. And then the isocontours of rotation are strongly tilted with respect to the rotation axis. So all of these different features must be relevant to the specific form of the solar dynamo that we see. And because the tachocline has the most shear, often it's assumed that this is the seat of the dynamo, the primary location where these flux tubes are formed. And then the problem is they have to traverse the entire convection zone. And so again, the question is this a viable scenario for the dynamo, where we have these flux tubes getting formed in the tachocline and then traversing this highly turbulent convective zone to emerge at the surface? So again, what do we know? And what we know is really concentrated, I would say, to the surface, because that's what we observe. And the surface dynamics we know pretty well. We can observe the convective patterns at the surface. This it's called granulation. So if you look at an image of the sun in photospheric intensity, say, you see that it's peppered with these convective cells. They have a length scale of about 1 million meters, a megameter, a velocity that's order Mach number 1 of a kilometer a second. And then amidst these structures are the larger magnetic regions. So the magnetic regions often form spots because they suppress the convective energy transport in the region of intense magnetic field. And the sunspots have length scales of about 30 megameters, field strength of about 1 kilogauss. Why am I going through all this? Well, it gives you a sense of the dynamics. The gas pressure on average at the photosphere is about 10 to the 4 pascals, and then you can plug this into calculate different forces. And so you can calculate the plasma beta which is the ratio of the gas pressure to the magnetic pressure, is about 0.3 within a flux tube. This means that the magnetic pressure is dominating. And in fact, the velocities, even though they're high, well, the density is low. And so the ratio of kinetic energy to magnetic energy is also less than 1. So the picture that you have of the surface dynamics with rotation and viscosity are probably unimportant because things are moving so fast. And the picture that you get is that magnetism is dominating within these flux tubes in about 5% of the solar surface, and in the rest, there's this very rapid Mach number 1 convection driven by pressure gradients and buoyancy. So that's good. We know sort of how the surface is working. We can simulate the surface. And then what do we know about the interior? And I put 3 question marks here because the answer is not much definitively. But there are clues. So the first clue comes from what's called supergranulation. So if you look at, this is a Doppler velocity image of the sun. You can also see these larger scale convective patterns, which typically appear in the horizontal velocity. So you can see them more clearly toward the edge of the solar disk. And these are larger scale than the granulation. And so the thought is that these are signifying motion a bit deeper in the convective zone, because to overturn, they need to extend fairly deep, maybe. And the supergranulation has scales of about 30 megameters, so much bigger than the granulation, and velocity scales of about 100 meters per second. We also think there might be what are called giant cells. So these are very large cells spanning the entire convective zone. This is a little schematic, I think from Featherstone Heinemann, 2016. And the idea is that we have all of these scales of motion in the convective zone with larger scales and small velocities. The giant cells may be rotationally constrained, in which case they form what's called Taylor or Bussy columns. We don't know the velocities of the giant cells, so that's one open question. The magnetic field, we also really don't know. So one major question is it these concentrated flux tubes everywhere? Is it space filling? Do the flux tubes form near the outer surface and then rise up, or do they form in the tachocline? What is the field strength? These are all kind of open questions. And the best tool at the moment we have to attack these questions, I think, is global simulation. So that's I think that's why we do the global simulations. And then finally, we do this force balance stuff. We don't really know how to do that because we don't know the numerator and denominator. And it's different than the surface because rotation is important in some places, probably deeper down. So basically, we know pretty well. We can simulate, don't know very well. The simulations have to inform what we think about the interior. Okay, so the broad theme of this is that there's basically 2 ways to attack this problem. You can simulate some very accurate, very high fidelity local simulations of the surface. Shin showed a great one that actually spanned the whole convection zone, so things are getting better, but in general, it's a local simulation. It's also local in time, so you can't run these things for very long. But the advantage of doing a local simulation is that you include all this complicated physics at the photosphere, like 3D, non-local, non-gray radiative transfer, which just means you keep track of all the photons as they move around the plasma. You can do full compressibility, so you can do Mach numbers order 1. You resolve a turbulent cascade. You can get buoyancy instability. So as we saw in the last talk, the flux tube rises to the surface and forms a magnetic region. That's something the global models can't do. So these are just examples from a Miram simulation from Matthias Rempel. What these models exclude is global flows, like differential rotation. There's a meridional circulation, which we didn't talk about. What I've been calling the Tachocline connection, the transition layer between the convective zone and the radiative zone. It's kind of because we can't do the large scale flows. And then I would say the biggest problem would be realistic boundary conditions. So we'll get more into that in the next few slides. And because you can't run these for very long and they can't be very big, you don't get a lot of the emergent behavior like a dynamo cycle. And then finally, self-consistency. You kind of have to impose some ad hoc physics at the boundaries in order to get one of these. You're only capturing a local portion of the star. The other thing you can do, and this is what I do, is global simulations. Some advantages of doing this is that you do get the global flows like differential rotation and meridional circulation. This is a 3D cutout from one of our latest papers, is showing this vortical helical convection in the convective zone, and then below this dashed line is the, well, there's a Tachocline region, and then there's magnetic field. So you can do dynamo, you can do dynamo cycles, and in this case we have a Tachocline, so you can do the Tachocline connection. And probably the biggest advantage of all this is it's self-consistent, as long as the self, I guess, is a cement block, because we're stuck in regions that are very laminar compared to the turbulent solar plasma. But we're solving the full equations. It's self-consistent. And the big problems with this is that we're excluding all the complicated physics of the photosphere. So we have this thermal conduction layer. We don't have any of the near surface physics. We also don't have realistic boundary conditions. So the top one is a perfect example. But also both of the boundaries are impenetrable, where in a real simulation, that's not the case. We don't have fast and small scale stuff because we can't resolve it. We probably don't have much of a turbulent cascade, and we don't have buoyancy instabilities. So there's a trade-off between these two approaches. And one pathway forward, which I think is sort of complicated, I mean, I don't want to be the one to attempt this, is to basically, maybe we can put these local models onto the global models and find some way to put patches of local surface models on these global models. I don't know how to do it. I think a lot of people have tried to do this, and with varying results of success, but I don't think we've had a very informative full simulation of the sun from the Tachocline to the surface. Not to say it's not impossible, I just don't know of a good way to do that, to capture the emergent behavior. So the question that I'm more interested in is basically how can these local and global models inform one another? And there, I think there's a lot of collaboration that can be had. For example, local models get the probably an accurate energy spectrum of the granulation. And so maybe one thing to do is we can use the information from a local model to impose some sort of near surface driving instead of the thermal boundary layer that's more representative of the actual radiative cooling. Additionally, the problem we'll see with the local models is a lower boundary condition, and maybe what we can do is impose background flows in the lower boundary in local models. These are just ideas of how we, the point is we should be talking to each other, because we're doing different pieces of the same problem. What we'd like to do is have the flux tube form self-consistently somewhere in the convective zone and then emerge all the way at the photosphere.
2 minutes, Loren.
Okay. Oh, whoops. Yep. Okay. Let me see. Let me try to wrap things up. The lower boundary condition is a problem for local models, global models. I think the biggest problem is the upper boundary condition. To talk about non-axisymmetric magnetism. Okay, if it's 2 minutes, I think I'll just interested in active longitudes. Okay, the final thing I wanted to mention is how can we link observations and global models and local models? So there's been some really interesting recent work by Sherbani and Sylvan, where they find significant time variation of a tachocline. And it doesn't seem like there's a simple link with to the 22-year cycle. And I'm wondering, I guess, if maybe this is a link with more irregular non-axisymmetric modes of the solar cycle. And so I'd be really interested to see where the work with active longitudes goes. In particular, is there some sort of cycle associated with the active longitudes? Is there any link between the polarity of active longitudes and their location? And I think there's a lot that can be learned from analyzing the non-axisymmetric components of the solar cycle. Okay, so I guess that's it. I think the recap is this stuff is very difficult. We do this because it's difficult, not because it's easy. And the sun has very intricate surface magnetism and dynamics, but the interior is much less well constrained. And so global and local models excel at different things. And there are some things that I think we can learn from observations, global and local models. We can have more self-consistent boundary conditions, maybe patch things together at the boundary of the photosphere. And then my personal feeling is that it would be great to explore the non-axisymmetric modes of the solar cycle and Tachocline confinement, which I didn't discuss today, but that I think also has to do with the non-axisymmetry. And then the recently observed Tachocline time dependence. Okay, sorry for sort of going down a rabbit hole, but thanks for your attention. I'm happy to answer any questions. I hope at least we get some good discussions out of this.
Thank you very much, Loren. That's an excellent scene-setting talk, and it's actually what this whole workshop is about. So thank you so much. Sorry to, in fact, to cut you off. You zipped by a couple of great slides there.
No, I sort of got distracted, but
no worries. So questions, comments for Loren? Todd.
Well, I figure I ought to say something. Where do you think coffees can play a role in the next year and a half, which is kind of the time scale that we have left? What do you think are some of the most ripe things for us to be working on in terms of the chatting with each other that you were talking about? And I know you kind of skipped over some of those slides, and maybe that was some of it. So this is your opportunity to go back.
Let's see.
Pick up on a couple of those ideas that you were thinking of.
I mean, my personal thing. So personally, I'm very interested in active longitude. So I think there's a lot that could be done between the Tachocline theme and the new the active longitudes working group, because what we're finding in the global simulations is that there are these non-axisymmetric modes that in some ways resemble the structures that we think could be spawning active longitudes if active longitudes emerge. And I don't know, I mean, the simulations are saying basically that the same magnetic structures that spawn active longitudes maybe can confine a Tachocline. And I guess what would be the observational implications of this? So I think that would be a great thing to work on. And the other thing I think obviously is the global and local models. I mean, this is a very difficult thing to do. But I don't know, there must be a way we can, I don't know, take one of Irina's simulations and take the near surface information of the convection and somehow incorporate that to get a better global model. I don't know. It's something I've thought about for years. How to do it, I'm not so sure. But I don't know. I guess those are the two things that I would feel are something that COFFIES would excel at.
Thanks.
Irina?
Yeah, thank you for excellent presentation. Actually, with Stella Box Code, we already have such capabilities to take data from global models, and we already tested this on Jochen Fan simulations. And I'm sure you're aware about paper by Chen, I believe, 2017.
Yeah.
We basically use the same approach, only difference from previous study, we are not doing any scaling. It is major difference. But everything else pretty much the same.
Okay.
So probably we should discuss later after.
Can I ask a does Stellar Box go down and to like the Tachocline and produce a Tachocline?
I'm running now
lower
this whole convection zone, but yeah, but I'm not going to discuss this today because it's too early.
Okay.
Too many problems associated with this, so we are solving them.
Let's see, Debian?
Hi, Loren. Thanks for the great talk.
Thanks.
I had a question. I love this connection between interior and photosphere simulations. I was planning to do something for different kinds of stars. So do you think other stars, which are like, let's say, smaller stars like M dwarfs, which are fully convective, could also give some insights for the solar purpose? Usually we use everything from the solar purpose and extend it to smaller stars in exoplanets. Do you think the other way can provide some insights?
No, for sure. I mean, one thing is I don't think the sun is necessarily typical in the sense that, you know, the flux tubes only cover 5% of the surface. On a lot of the fully convective M dwarfs, it's 100%. And so, you know, why is that? Is it just because they're smaller, so there's more surface area, there's less surface area? Is it because they're fully convective? So yeah, I mean, I think the reverse is true. The more we learn about other stars, I think the more we kind of always assume that the sun is the benchmark, but the sun has life around it, and that might be unique. And so there's a lot of, in areas in which the sun may be less active than other stars, it might be, the magnetic field might be atypical.
Right. Yeah, I just wanted to point out a few observations of the TRAPPIST system. There have been a lot of planets identified around that system, and there are studies on activity of the specific star with a bare rock planet and then atmospheric planets, like planets with atmospheres as well. And based on how they transit the planet, they kind of block out spots at different latitudes. So they could block out polar spots versus equatorial spots, giving more information. So I was thinking about these kind of stars, and that's
interesting. Can you get differential rotation from that, or
not yet, but
maybe
more measurements are coming with JWST, so maybe sometime soon.
Cool.
M stars have a Tachocline. Later M stars wouldn't. I think later M dwarf stars wouldn't have a Tachocline. Early ones have.
No, probably not.
Yeah, early ones have like a smaller stratified interior.
Right.
Okay. Thank you so much.
Yeah, sure.
Yes, thanks again, Loren. So so let's pause there for a moment and get a quick 15-minute coffee break in, and we will reconvene for another scene setting talk at 5 to the hour, not the hour, but 5 minutes prior. So we'll take a quick break and we'll see you all in a moment.